อยู่นะครับก็ขอเป็น absent แล้วกันนะครับ absent moment let me check okay this fine this is M605 โอเคเพราะฉะนั้นต่อไป18นะครับปันณทัศน์นะครับ
ครับอยู่ครับ
ณทัศน์อยู่ตรงไหนนะครับเปิดไมค์เห็นแล้วครับปันณทัศน์ต่อไป19นนทกรครับ
มาครับอาจารย์ครับคือที่นั่นผมไม่แน่ใจว่าเขาเตรียมIELTSเหมือนกันหรือเปล่าแต่น่าจะใช่นะครับ
แล้วคุณใช้คำว่าไม่แน่ใจแล้วผมควรจะทำยังตัวไงนะครับ
เดี๋ยวผมเช็คใบลาให้แป๊บ
ครับจริงๆเพื่อนไม่ควรเข้าไปเช็คนะครับมันเป็นธุระของเขาตัวเขาเองเขาควรที่จะเป็นคนแจ้งผมนะครับนะมันเป็นธุระของเขาโดยตรงนะครับอย่างที่ผมแจ้งแต่วันแรกนะว่าถ้าลาเนี่ยควรแจ้งผมก่อนนะครับเราอยู่ใกล้ๆกันนะครับอะไรทางไลน์ทางอะไรอย่างเงี้ยครับคุณเดี๋ยวผมเปิดไลน์เครื่องนี้ไว้ก่อนครับเพื่อเช็คครับว่าเกิดอะไร
อาจารย์ผมเช็คแล้วครับมีใบลาIELTS
เดี๋ยวครับผมดูที่ไลน์กลุ่มของเราก่อนนะว่าผมไม่รับทราบข้อมูลว่าผมไม่อยู่ในไม่ได้ดูที่ไลน์หรือว่าอย่างไรครับใบลาทัศนัทครับ605เราเรียนทางช่องไหนเหรอครับอาจารย์ผมสตรีมไปที่ YouTube ด้วยนะครับตอนนี้ YouTube ไปด้วยแล้วก็มีหลักๆนี่นะครับ2ช่องทางครับแต่เหมือน YouTube ว่าจะไหลไม่ค่อยดีนะจะกระตุกหรือเปล่าครับก็เนื่องจากว่ามันมีมีดมาด้วยครับก็แป๊บโอ้มันวิกฤตโอเค don't worry it's poor condition 18นะครับปัณทัศน์ใช่ไหมครับปัณทัศน์เดี๋ยวนะครับพฤตินันนี่สรุปคือมีใบลานะครับผมจะได้ลงให้นะครับอย่างถูกต้องโอเคคนลานี่จริงๆน่าจะแจ้งผมก่อนครับ What happens เกิดอะไรขึ้น12 number 12นี่นะครับโอ้โหลากันหนักมากครับ18ปัณทัศน์นะครับเหมือนตะกี้ได้ยินเสียงอยู่ตรงไหนครับปัณทัศน์ครับ
ไปแล้วครับ
ไปแล้วใช่ไหมครับต่อไปนนทกรไปแล้วใช่ไหมครับหรือว่าไงผมลืมแล้ว
ใช่ครับ
19ไปแล้ว20ว่าลินทรครับลินทรอยู่ไหมครับวลินทร
ไปไปเตรียมตัวสอบเหมือนกันครับ
คนที่บอกว่าเตรียมตัวนี่ผมไม่เห็นรับเอกสารอะไรที่เป็นทางการอะไรคุณเลยนะครับเหมือนเราพูดกันไม่ค่อยรู้เรื่องครับคือผมบอกว่าถ้าลาก็ให้แจ้งก่อนนะครับคุณก็ยังเฉยๆอย่างเงี้ยนะครับวลินทรนะครับเคมากคือผมให้เยอะนะครับการเข้าเรียนนะครับคุณโปรดทำตัวให้คุ้มกับคะแนนที่ให้หน่อยนะครับthe number 21ละวิพลครับวิพลอยู่ไหมครับ
อยู่นี่ครับ
โอเควิพลอยู่ทะเลนะครับโอเค22วาลินทรีนุภาพ
ครับผมอยู่นี่ครับ
โอเคเห็นแล้วครับเห็นหน้านิดนึงเต็มเลยครับโอเคต่อไป23คนสุดท้ายครับพระสิทธิ์ครับ
มาครับอยู่นี่ครับ
โอเคเห็นแล้วครับ
ครับผม
ทะเลเหมือนกันครับโอเคก็ประมาณนี้นะครับ เดี๋ยวผมปรึกษากับดร.ชกสลันครับอีกรอบหนึ่งครับ เบื้องต้นความเห็นครูจอยประมาณนี้แหละก็ขออนุญาตเข้าห้องน้ำแป๊บนึงครับ ผมยังไม่ได้เบรกจากห้อง604เลยนะครับครับมีอะไรไหมครับ
ป่าครับไม่มีนะครับ
โอเค
อาจารย์ครับ
ทางใครเอ่ย
พอดีผมมาแต่ไม่ขึ้นว่า absent นะครับ
ใครนะลูก
เลขที่22ครับผม
เลขที่22คือ
วลิน
ว
ครับ
รินทร์วรินทร์มาเหรอคะ
ครับผมอยู่เนี่ยครับ
ไหนเอ่ยครูไม่เห็นหน้าเรา
นี่ครับ
วรินทร์อ๋อโอเค เมื่อกี้อาจารย์เขาเช็ค absent ไปเหรอ
ครับผม
โอเค เดี๋ยวรออาจารย์บำรุงมาเดี๋ยวบอกอาจารย์
ได้ครับ
ครับ มาหรือยังอาจารย์บำรุงมาหรือยังคะ
เชิญครับ
อาจารย์วรินทร์มาอยู่ค่ะอาจาร
เล
ย์
ขที่22ครับอาจารย์
รอครับแล้วตะกี้ผมไม่ได้เปิดไมค์ใช่ไหมไม่ทราบว่าคุณพูดใช่ไหมครับหรือว่า
ผมพูดแล้วครับตอบอาจารย์ว่าวลินมาครับ
แล้วครับขออภัยด้วยครับ
ครับผม
โอเค present ก็จะประมาณนี้ครับออกมาหน้าตาประมาณนี้ครับเปลี่ยนให้แล้วโอเคก็เรียนคุณนะครับว่าเอาที่มันง่ายๆแล้วกันนะครับคือไม่ต้องทำรายงานครับแต่ว่าเช็คชื่อเป็นหลักนะครับขอความกรุณานะครับคุณพร้อมอยู่ที่หน้ากล้องนะครับก็คือเราจะใช้ทางนี้เป็นหลักนะครับส่วนผมไม่รู้ว่าจะช่วยได้หรือเปล่าครับผมสตรีมไปที่ YouTube ด้วยแต่ว่าตอนนี้มันจะค้างๆเพราะว่าอินเทอร์เน็ตถูกใช้ไปกับ Meet นะครับส่วนคนที่บอกว่าไม่ชัดอะไรยังไงก็ผมไม่ทราบเหมือนกันนะว่าเวลาสลับกล้องมาที่กระดานแล้วจะเป็นอย่างไรโอเคso let's get into our lecture note we are somewhere here right it's the story about the Snail Law right ใช่ไหมครับเราถึงที่ Snail Law หรือเปล่าเลยใช่ไหมครับเราอยู่ที่ Snail Law นะครับ
น่าจะใช่นะครับ
โอเค and let me take a look at the sharp monitor so it's laptop right now okay maybeโอเคอยู่ที่หน้าไหนครับหน้านี้หรือเปล่าที่เรียกว่าdid we arrive at the index of refraction is that correct ใช่ไหมครับ let me check okay the index of refraction right ถ้าถูกต้องนะครับผมก็วางกันหน้านี้เลยนะครับไม่รู้ว่าซ้ำหรือเปล่าครับ Okay, the index of refraction is a ratio which is introduced in physics so that we can know the relative speed of many things, of many substances or many of several matters, and it plays a central role in geometrical optics. It is actually defined as the ratio between the speed of the light in vacuum. Okay, please note that we are talking about the same thing, which is the speed of the light, but in different materials or in different substances. But the index of refraction is defined as the speed of the light in the vacuum as the numerator, and at the denominator we consider the speed of the light in a certain in a material that we are interested in. So it's denoted by V. Okay, C doesn't change. Okay, with any other substance. Okay, C it's the property of the light speed only in the vacuum. So we go ahead, and here you can see what happens in this one.มีคนทักที่ไลน์กลุ่มนะครับว่าไบลาทุกคนไอเอลนะครับคนชื่อเฟียสนะครับโอเคพร้อมลายเซ็นดร.โชคสลันครับ It's fine. I think. Okay. Here you can see the indices of refraction for different materials. The first one is the first type is liquid. Okay. And the second type is the first type is solid. The second one is liquid, and the third one, the last one, is gas. Okay. Okay. What I need to mention is that when the light propagates through matter which is different from the vacuum, its speed is going to be lower. Okay. The light will propagate slower than that in the vacuum. Okay, what is the reason behind that? Because in the vacuum we have nothing. Okay, it's only an empty space, and you know that every substance or every material or matter is full of atoms, right? นะครับทุกสสารนะครับก็เต็มไปด้วยอะตอมใช่ไหมครับ so the basic particle is atom, or even you consider the bigger scale, for example, molecules. Okay, every matter has atoms, but in vacuum we don't have any atom. It's only an empty space, and when the light propagates through atoms, several atoms, it's going to be obstructed. Okay, it has some obstacles, so that make the impedance for the light to propagate in this one. Okay, the velocity V. It makes the speed of the light in that material slower. Okay, and that's the reason behind it. And you know that the index of refraction is the speed of the light divided by the ratio between the speed of the light in the vacuum to the speed of light in a material. So as I said, as being said, the speed of the light in any material is going to be lower than this thing. Okay, the speed of light in the vacuum. So you have something divided by something smaller. It means that this ratio is going to be bigger than 1. Okay, it should be it should always be greater than 1. So what you can see in this table is that all the values here are greater than 1, right? And it's called indices of reflection for different materials. And let's consider the first type of the matters, which is solid. Okay, solid is full of dense molecules or dense atoms. Okay, sorry for the ขออนุญาตเช็คตรงนี้นิดนึงครับเช็คว่าออกไปยังไงครับถึงตอนหนวดคลาสเนี่ยเห็นนะว่าภาพที่ออกไปคืออะไรนะครับผมจะได้ทราบว่าเกิดอะไรขึ้นบ้างครับโอเคand the most dense state of the matter is solid, right? In this phase, you know that there are different phases. For example, solid, liquid, gas, and something else. What else? It's plasma or ion. Okay, there are maybe 5 states or phases of that. But what we are going to consider are only 3 phases, which are solid, okay, liquid, and gas. As you may know, the solid is full of dense atom. Okay, the atoms stay quite close to each other and makes the strong bonding force between or among those atoms. And because the atoms are quite close to each other, there will be much obstruction when the light propagates through that. Okay, what we are considering here are only the transparent material. Okay, ภาษาไทยเรียกว่าวัตถุโปร่งแสงนะครับคือแสงผ่านได้เท่านั้นนะ We don't talk about the material like a metal or something else. In those materials, the light cannot propagate through to them. And what we consider here are only the transparent materials. These are in solid phase, and because of the dense molecule or dense atoms, it has much obstruction to the light to propagate, and you can guess or you can realize that the speed of the light in these kind of materials, okay, which is the most dense phase of materials, will have slowest, okay, or slower speed of the light. And when you have slower speed of the light, that material, okay, this one is much lower than the numerator, the ratio is going to be large. Okay, and as you can see here, for example, diamond, which is really, really strong. Okay, it has the most, I think the highest strength of material that, you know, we use diamond to cut even the metal, right? Because diamond is stronger, has much greater strength than certain kind of metals, because of their dense molecules or atoms. You can see here that the velocity or the speed of the light in the diamond is very, very small. So that makes this ratio to be very large, and you can see the value is even greater than 1. Okay, it's 2.4, blah blah blah. And most of these have much lower speed for the light to propagate, and this ratio is going to be large. Let's take a look at the liquid phase. Okay, like benzene, ethyl alcohol, water, or even glycerin. Okay, the density of the atoms or molecule of those matters is less than the solid phase, and that's why you can see the lights will have it's going to have higher speed in these materials, okay, in the liquid phase, but it's quite close to the one in the solid, okay, it's not much different, but in average, you can see that these values are quite close to this one, okay, in the solid phase, but it's a little bit lower than the one in the solid, okay, that's the reason behind why the speed of the light in liquid is lower than that in the solid, okay, because the atoms here is more separated from each other. The atoms are more separated from each other in the liquid phase. And let's take a look at the last one, okay, which is noticeably separated, the gas phase, okay, the atoms or the molecules of any gas, okay, are quite far away from each other, and it brings us less obstruction for the light to propagate. And this is the reason why the light in these materials can propagate quickly, okay, and the speed of the light in the gas phase is quite high. It's quite high such that it's close to the speed of the light in the vacuum, okay. In this scenario, there is no atom to obstruct the propagation of the light at all. But in the gas, okay, we have some atoms, okay, but it's not so dense, okay. The density of this phase is not as high as liquid or solids. So the speed of the light in the gas phase is quite close to the speed of the light in the vacuum, okay. And what you can see is that, of course, the velocity of the light in any matter should be less than the speed of the light in the vacuum. You can see that the light speed here should be a little bit less than the speed of the light in vacuum. And when you consider this ratio, you have this amount and something which is a little bit less than that. So this one is going to be quite close to be number one, but it's still greater than one, okay. And that's why we can see the value here 1.00293, 1.00045, okay. It's very close to number one, but in the example, when we solve the problem, we are going to use this value simply, okay, with the number one, okay. We don't need to pay attention to the digits of the several position of the points here, okay. We don't need to include the detail 293 or 45 at all, okay? We just use number one simply, same as the speed of the light in the vacuum, okay, even it's not one, okay, but for simplicity we are going to use number one, okay. We have considered the indices of reflection, okay, in these three phases. This table is taken from book number 3, and this one is taken from the book number 4 on this figure, okay. This value is measured by the light of vacuum wavelength 589 nanometer, okay. If you use different light, okay, which doesn't have the wavelength like this, you may get something else, okay. Those may not be this value, okay. This table is valid for only this wavelength, but for simplicity, we are going to use this value for several applications, even the light doesn't have the wavelength like this. And in this table as well, okay, they use the same wavelength of the light to measure the index of refraction, okay, 589 nanometer again. And this table includes only the solid and liquid phases, okay. There is no indices of reflection for the gas at all. And you can, in the homework, okay, if we have a homework about this, you can choose any table, okay, as you like. Just write down the reference or where you have taken the resource from. Okay, as you know before, in the basic propagation of the light in the material, we have the relationship in equation number 12, right? In I need to remind you something, okay? We have this relation, and after that, we have sine theta 2 by sine theta 1 equals V2 by V1, okay? That's the result from this model. And recently, we have just considered the index of refraction, which is N equals C by V. Okay, we will go ahead with this relationship to see it in different form. Okay, let me change the microphone to the wireless one so that I can bring you to the whiteboard. Okay, I'm going to derive something.ผมใช้ไมค์อันนี้นะครับทุกคนได้ยินนะครับ extend microphone ฮัลโหลครับได้ยินนะครับโอเคก็มาใช้ไมค์เดิมก่อนครับนึกว่าจะใช้ไมค์ wireless ได้นะครับโอเคไม่เป็นไรโอเค no problem Okay, let's. No, I need to change the camera. So. Meet, and then stop presenting. ครับมาที่กระดานนะครับไม่ทราบว่าคุณเห็นกระดานหรือเปล่านะครับไปไหมครับกล้องที่กระดานไปไหมครับวิดีโอno I need to switch it from camera โอเคไปไหมครับไม่ไปนะครับไม่เป็นไรเดี๋ยวเซตตรงๆนี่นะCamera number 2. Okay, that's it. Okay, we are here on the whiteboard and going to go ahead with that relationship, and we will substitute the index of refraction into the first relationship sine theta 2 by sine theta 1. ไม่ยังได้ยินอยู่นะครับไม่ยังได้ยิน Okay, we are considering the light that is propagating the light that is that's propagating in this direction, okay, from from the first material, and it propagates through the second material or substance. And before that, we have the relationship. I hope that you can see the camera properly. Okay. Oh no, it's impossible. Okay. Anyway, psi theta 2 by psi theta 1 equals V2 by V1. Okay, V1 is the speed of the light in the first substance, and V2 is we have V1 here. Okay, the speed of the light in the first substance, and we have V2 as well. V2 it as the speed of the light in the second substance or the second matter. And recently we just introduced the index of refraction, which is N equals C by V, right? And because we are talking about the speed of the light, so we need to manipulate this equation. We move V from the right hand side to the left hand side, okay, at the denominator portion to the numerator on the left hand side, and we move into the right hand side at the denominator. Of course, what you get will be V is equal to C by N. Okay, and in this equation, only variables V and N, okay, will depend on the substance, because C is the velocity or the speed of the light in the background. Okay, it has nothing to do with substance 1 or substance 2. Okay, no subscript for C at all. So in both substances, we would have V1 equals C by N1. Okay, and V2 equals C by N2. And what we are interested in is the ratio between V2 and V1, right? So you can see that if we write down V2 by V1, okay, which is the right hand side of this equation, it means that we just leave this ratio together and divide it by the big straight line, and it's going to be C by N2. Okay, and this the lower one, the denominator is going to be the result from the first equation, which is C by N1. Okay, and of course, what you get further is that C by N2, okay, as the numerator, and the denominator will change their position, the position of the elements. Okay, here you have N1 by C. Okay, and you can find that there are C above, okay, at the numerator position, and also below here the denominator position, so we can cancel them, and finally we would get N1 divided by N2. Okay, we start from V2 by V1, right? And we would get this expression. Okay, this one. And the result in equation number 13 นะครับไม่ใช้ได้นะครับพอได้ยินอยู่นะครับ and what else I need to bring you back to the monitor. Okay, okay, we have V1 by V2 in terms of indices of refraction. Okay, N2 by N1, or even V2 by V1. Okay, it's just the different the opposite subscript for numerator and denominator. And now we arrive at the principle of geometric optics. Okay, principle of geometrical optics. In order to consider the principle of geometrical optics, we will use this figure as the model. Okay, as the model for us. Okay. This is the model in order to consider the principles of the geometrical optics. Okay, there will be 3 rules. Okay, 3 rules. The first rule is that, of course, let's talk about this figure first. So the mechanism of this experiment is that you let the light go in this direction. Okay, it starts from any source. Okay, in a far field, so the light is going to propagate as a narrow beam or only a line like this. Okay, it propagates from the left to the right, and the blue area here is known as the first substance. Okay, let's say it's substance A or substance number 1, as you like. And on the right side, it's denoted by yellow area here, which is the second substance or substance B or substance number 2, as you like. Okay. The incoming light, okay, propagates in this way, and it's called incident ray. And of course, when 2 substances stay close to each other like this, okay, this one is stay next to the first one, there will be a border. Okay, this one is called a boundary, and let's say the boundary has a smooth surface, and its contact can be represented by a straight line like this. And this is important. Okay, the boundary is important. When the light propagates in this way, okay, as the incident direction, there will be another component, which is this one. Okay, you know that you have ever heard in the past 2 years there will be refraction. Okay, for example, momentum and so on. Okay, there you can see the reflection after the crash, and this is the same thing when the light hit the atoms of some material, is that you would get a reflecting component. Okay, which is again in the narrow beam manner, or even in the straight line as the point like this. Okay, you get the reflecting component, which is called reflected ray. And let's talk about the angle first. Okay, we have, of course, this is the boundary line, and there is another line. Okay, this line is made with 90 degrees from the boundary line, and this one is called normal. Okay, the normal line is 90 degrees from the boundary line. Okay, and when we are talking about the angle of several components in the light propagation, we would measure the angle from or with respect to the normal. Okay, the normal axis. In the incoming ray or incident ray is measured from the normal axis. This, okay, and for the second component, the angle is also measured from the normal axis. So the first one is called theta A. The reason why we say theta A is that this is the angle measured at the substance A, okay, or the first substance. That's why we use the name of the first substance, and as the subscript here for the angle. And for the second component, we won't use theta A anymore, okay? Even they are still in the same substance, in the same side material, but we will replace A by R, okay? This R means reflecting or reflection. And what else? There is another component, okay, when the light propagates through the second component, and let's assume that the second component is a transparent material, okay, the material that allows the light to go through. And this angle can also be measured from or with respect to normal, and we would not say theta A anymore, okay, because it's not on the substance A side, but rather here it's on the substance B side. So that's why we say theta with the subscript B, okay, because this angle is measured in the substance B. And let's talk about the first rule in the principles of the geometrical optics. The first rule is that, of course, you know, there are 4 lines, right? There are 4 lines. The first line is incident ray. The second line is reflected ray. The third line is reflected ray, like this, okay? But one more line, which is also important, is the normal line here, okay? This line is made with 90 degrees from the boundary line, okay? The first rule of the principles of geometrical optics is that these 4 lines, okay, line number 1, number 2, number 3, and number 4 will all lie in the same plane, okay? That's the first agreement between us. These 4 lines, this line, this line, and this line, and also this line are in the same plane, okay? It cannot be out of the plane, okay? And that's we cannot analyze in just what we cannot analyze in the next pages. Okay, that's the first rule in geometrical optics. Let's talk about the second rule. What is that? Of course, we know that we have the incident angle, which is theta A, okay? The angle measured from the normal for the incoming ray or the incident ray. And we have another component, which is the second component, the reflecting one, okay, reflected ray. And the angle is measured also from the normal, which is denoted by theta R, okay? The second rule of geometric principle is that the incident angle will be equal to the reflecting angle, okay? This one can be expressed, this relation can be expressed like this, okay? The angle, the incident angle is the same as the reflecting angle, okay? These 2 angles are equal to each other. That holds true for any cases, okay? And let's talk about the third rule, okay? The first rule is that these 4 lines, 1, 2, 3, and 4 are in the same plane, okay? The second rule says that the incident angle is equal to the reflecting angle, okay? Theta A and theta R are the same, okay? Are equal to each other. And the third rule is that the third rule talks about the relationship between the incident angle and the outgoing angle, or it's called reflecting angle. Okay, what is the relationship between this? Most physicists realize that the third rule in geometrical optics is what we call Snail's law. Okay, what is Snail's law? Okay, this is the first rule, the second rule, and here is the third rule. Okay, the law of refraction, and this law seems to be discovered by this person, Willebrord Cornelius. Okay, it's not the typical name nowadays. It's the name in the Latin generation. Okay, before that, in Europe, they use the Latin as the scientific language. Okay, even now, if you study medicine, for example, in the country that I have been in Germany, you need to study Latin language as well. Okay, but Latin is not a speaking language anymore. It's not spoken language. It's the ancient language, but it's required for some branches at the university. You need to study it, but there is no speaking opportunity for you to speak Latin anymore. It's an ancient language. It's the same here. Willebrord Cornelius is the name written in Latin style, and nowadays we just say it's Snail's law. Okay, we don't need to put IUS. Okay, IUS is an ending word for the Latin name. Okay, nowadays we just simply use Snail's law. The important thing for the Snail's law is that it's derived from what we have seen on the whiteboard. Okay, let me take you to the whiteboard. นะครับขอหยุดพรีเซนต์ครับแล้วกลับมาที่กระดานครับไม่รู้ว่าคุณจะได้ยินหรือไม่เดี๋ยวดูก่อนนะครับว่าthis one ก็การดีไลท์ก็ง่ายมากครับไม่รู้ว่าไม่ไหนใช้ได้ครับHello. No. So I need to use the same microphone. Okay, no problem. Just get back to the whiteboard. Okay, we are going to derive the results from the Snail's law. You can see that the ratio V2 by V1 is N1 by N2. Okay, it's in the opposite way for the subscript at both positions. This is actually the right hand side for the former relationship, and if you substitute these results into this equation, what you get will be sine theta 2 by sine theta 1, and we just leave this ratio on the right hand side, and it's N1 by N2. Okay, in the lecture notes they say to as the letter B. Okay, and number 1 as the letter A is the same thing. Okay, it's just the name of each substance. But the important thing is, if you want to get the same exact result, I can express it in AB terms. This is okay, so that you will not get confused. What you have will be sine theta B นะครับไม่ทราบว่าชัดหรือเปล่านะครับถ้าอยู่ที่ YouTube น่าจะชัดกว่ามั้งครับโอเคsine theta B and sine theta A equals NA by NB. Okay, and what you can do further is that you can move the denominator here to the left hand side, and you can move the denominator on the right hand side to the left hand side to the right hand side. So what you get will be NB sine theta b equals NA sine theta A. Okay, and that's the Snail law. Okay, Snail's law is that says that the product between index of refraction of one material to the sinusoid of the angle at one side will be the same as the product of the index of refraction and the sinusoid of the sine function of the angle on another side. Okay, and that's the Snail law. We need to go further with the next property of polarization in two materials, right? I need to share the screen like this. ไปไหมครับไปนะ Okay, now we will consider the polarization of unpolarized light. Okay, actually it's partial polarization. The partial polarization can happen in reflection. And let's take a look at this figure. You have here the unpolarized light. Okay, and as we know earlier, the unpolarized electromagnetic wave is the light that has different directions of the electric fields. Okay, here you have electric fields in different angle, and these lights, and of course the light is a kind of electromagnetic wave, and the electromagnetic wave is a transverse wave. So you can see that the propagation direction of the light is 90 degree to the E field, okay, to the electric field in every direction. But anyway, our target is to cause the direction of the light propagation, which is in this way. Okay, it starts from source, and it has the narrow beam, or it's just in light position, and then there will be another, which is the second component, which this one, okay, refraction component, and another component, the last one, the third one is this one. Okay, that's the component that propagates to another material. Okay, we have material A, let's say in this case the air. Okay, and material B, which is denoted by the blue surface here. Okay, and there will be some conditions that take place in this experiment. Oh no, internet ผม what happens? Can you see it? Oh my. microphone โอเคทุกคนพอได้ยินนะครับขออภัยด้วยครับอินเทอร์เน็ตหลุดนะครับงงมากว่าเกิดจากอะไรนะครับไม่เข้าใจนะครับ sorry for that stand extend microphone ฮัลโหลครับโอเคI need to change the speaker as well right speaker โอเคอันนี้ใช้อินเทอร์เน็ตส่วนตัวนะครับเครื่องนั้นอินเทอร์เน็ตมหาลัยใช้ได้นะครับผมงงมากครับแต่ว่าเครื่องหลักเนี่ยครับอยู่ดีมันก็หลุดไปโอเคOkay, let's get back to our story, which is this one. I need to I'll share the monitor, right? I need to share the monitor. This one. Okay, here. You have the unpolarized light, okay? And it propagates like this, as same as before. Okay, there will be two components. The first one is the reflecting component. The first one is reflecting component. The second one is the reflecting components. Okay, this one just propagate through the second material. Okay, let's say this is the B material B, and above the material B we have, let's say it's the air. Okay. And let the name of the air as the subscript A. Okay, the subscript A stands for the name of the material, which is the air. And the important thing of this figure is that it's quite spatial from what you have seen. From what you have seen here, okay, it's okay, before that, you know that the relationship between theta A and theta I is that both are equal to each other. And there is the relationship between theta A and theta B, right? It's psi A and psi A divided psi B equals VA by VB. And it's equal to NB by NA, right? And you get the Snail's law, okay, which is this one, okay, the product of n and psi of each material is the same as the product of n and psi for another material. ปาฏิหาริย์นี่มีเพื่อนมาเรียนด้วยหรือว่ายังไงครับหรือว่าเพื่อนร่วมคลาสหรือว่ายังไงเอ่ย
เพื่อนที่มาทำงานด้วยกันครับ
โอเคผมก็นึกว่าเพื่อนอยู่ในคลาสนะครับthere are something special that happens in this in our scenario. Okay, we are talking about the polarization of electromagnetic waves. One thing, as you know, the incident wave will be the same as the reflecting angle. Okay, the angle of the incident component will be the same as the angle of the reflecting component. Okay, that's what we know from the second law in the principles of geometrical optics, right? And this is the reason why you can get a theta p for this one and theta p for this one. Okay, but in a special case, okay, for a certain value of theta at the incident side, at the material A side, if the incident angle is equal to a spatial value, which is theta p, there will be two features. The first one is that, of course, I need to mention that the incoming ray, the incident light, and the reflecting ray or the reflecting light, and the third one, the reflecting lights or the reflecting components, and also the fourth one, as actually the normal line here, are all in the same plane, and that plane is called plane of incidence, okay, which is the yellow area here โอเคนะครับทุกคนเห็นอยู่นะครับ okay, the yellow area here, it's called a plane of incidence, and another plane that we need to know is this one, okay. This is the plane where we have the contact between the air and the matter B, okay, or the matter number 2, and this area is called reflecting surface, okay. The plane of incidence will be perpendicular to the reflecting surface, okay. That's the basic thing you need to know. And the next one is that all 4 lines such as incident ray, reflecting ray, and reflecting ray and normal will be in the same plane, which is called plane of incidence. And one more special thing that happened in this scenario is that of course you know that you start with the unpolarized light, okay. The E field points in many different directions, but after the reflection with a certain value of angle at the incidence here, you will get the light that has only the E field in a horizontal way like this, okay. This line, the E field, the pink one here, will be parallel to the surface, okay, the reflecting surface, and this line, okay, the E field will be perpendicular or 90 degree with 90 degree to the plane of the incidence, okay. And that's the first thing. And there will be only this arrangement of the E field, okay. The E field will be only in horizontal way, and it means we have a linear polarization of the light in this component, okay. It means that the reflecting light is going to have linear polarization, okay. The E field will be all the time in horizontal arrangement like this, okay. And the intensity of the reflecting component will be, of course, less than this one, okay, because some of the energy is absorbed in the boundary or in the second material. And let's take a look at the third component, which is the reflecting ray, okay. The light can also propagate into this one. The surprising things also happens in the third component is that the light in this component, the reflecting ray, will have 2 axes for the E field, okay. The first E field, okay, the first alignment of the E field is in the same way as the reflecting component, okay. The E field will be parallel to the reflecting surface, okay. This one is parallel to this one, parallel to the reflecting surface, and this component will be perpendicular to the plane of the incident, the yellow one, okay. And there is also another component where the E field is in the same is parallel to the plane of the incidence, okay. And that's the surprising thing that happens, okay. We need to mention that these 2 scenarios will happen when the angle of the incidence is exactly equal to a certain value, which is called polarizing angle, theta p, okay. In this text they say reflected or transmitted light is strong, okay. The strength or the intensity of the light in this component is stronger than this one, okay. As you can see, there are two types of the light, okay, with polarization, is linear polarization in this way and in this way. And the light is slightly polarized, okay, because there are 2 mixed types of light, okay, with the E field in this way and the E field in this way, okay. And the plane in figure 39, the plane containing the incident and reflected rays, incident and reflected rays, and also the normal, okay, this is the normal, are called plane of incidence, okay, the yellow one here. This is the explanation to figure 39 again, and it's called plane of the incident. The angle of the incident is called polarizing angle. What time is it? I think it's the time is over, but let me just complete this page, okay. And the angle of the incident is called polarizing angle, okay. This kind of E field arrangement, okay, and this one will happen only when theta is equal to a certain value, which is theta p. You will have a chance to get to know what exactly the value of theta p is in the next section, which is the equation by Brewster. Okay, but I think we need to finish right now. The light will reflect only when its electric field vector E is perpendicular to the plane of the incidence. Okay, only the light that has the E field parallel perpendicular to the plane of the incident, okay, will be reflected. Okay, other components cannot be reflected from this boundary, and that light should be parallel to the reflecting surface. Okay, it means these components. And I think we need to finish right now, right? จะต่อไหมครับ หรือว่าเลิกละอยากเลิกแล้วครับเพราะว่าเวลามันเลยแล้วหรือว่ายังไงครับ แล้วแต่คุณคือถ้าปล่อยผมไปต่อผมก็ไปได้เรื่อยๆครับโอเคไหมคุณอยากเลิกหรือคุณมีธุระหรืออะไรไหมครับฮัลโหลครับทุกคนได้ยินผมนะครับหรือว่ายังไงเอ่ยครับ
ได้ยินครับ
คุณเราจะเลิกเลยนะเพราะว่าเวลามันเลยแล้วหรือว่าจะให้ผมต่อรูปนี้
ก็ได้ครับ
เลิกเลยนะครับโอเค then see you on Friday right พบกันวันศุกร์ที่จะถึงนี้ครับไม่มีการบ้านครับเดี๋ยวการบ้านสั่งวันศุกร์แล้วกันเพราะว่าสั่งวันพุธแล้วคุณส่งวันศุกร์คุณจะเครียดเพราะคุณมีเวลาทำแค่วัน2วันใช่ไหมครับพอผมสั่งวันศุกร์แล้วคุณส่งวันศุกร์หน้าคุณมีเวลาเต็มที่เลย1สัปดาห์เอาอย่างนี้ดีกว่าไหมครับคุณจะได้ไม่เครียดเนาะนะครับ
ครับ
โอเค then see you on Friday สวัสดีครับบ๊ายบายครับพบกันวันศุกร์ครับStop recording. Stop recording.